Welcome back to Very Ordinary Differential Equations. In this lecture, having learned how to take Laplace transforms of step functions and products of step functions with continuous functions, we will learn how to solve differential equations with piecewise continuous forcing functions. Let's just refresh how step functions behave. So a piecewise continuous function can be represented as a product of step functions with continuous functions. Then we had our second shifting theorem, which provided a convenient way to take a Laplace transform of functions of this form, a step function times a continuous function, provided that they have been translated by the same amount. Specifically, the Laplace transform of this product would just be an exponential e to the minus s tau times the Laplace transform of the unshifted g of t. So what we should try to do is represent a piecewise continuous forcing function in terms of step functions times functions where they have been shifted by the same amount. Now we also had a theorem that told us how to take the Laplace transform of a step function times an unshifted function, but when taking the inverse Laplace transform later, the other form will simply be more convenient. So suppose you have a forcing function which is piecewise continuous in this manner. What we want to do is develop a general way to represent it as a sum of various terms, step functions times shifted functions. So usually this is going to end at some index. It's usually going to be finitely many pieces, but sometimes it might actually be infinitely many pieces. So first what we do is we write this as a product of step functions in the following way. This is our standard approach that we had in the previous lecture. So the function begins at f0. Then at time t1, we cancel f0 and introduce f1. Then at time t2, we cancel out f1 and introduce f2, etc. So here was our general way of writing this piecewise continuous function. What we're going to do is denote g sub I of t as f sub I of t plus ti minus f sub I minus 1 of t plus ti. So they have the same shift, but it's a difference of two different f's. Then go ahead and by definition set t sub 0 to be 0 and g sub 0 to be f sub 0. So what we end up seeing is, here we have f1 of t minus f0 of t. That's just going to be g1 of t minus t1. Similarly, f2 of t minus f1 of t is this difference of g2 of t minus t2 and so forth. So what we've done is we've taken each of these parenthetical terms and represented them as a single function shifted by the exact same amount as the step function. And at this point, we can take the Laplace transform fairly directly because we have made each term match the form of the second shifting theorem. Once you've done that, hopefully you can solve the differential equation that you began with. For our first example, let's solve an initial value problem. Y double prime is 4 minus t from 0 to 5 and negative 1 past that point. Y of 0 is 0 and y prime of 0 is 15. So this might model an object that begins at a height of 0, y of 0 is 0. It has an initial velocity of 15, y prime of 0 is 15. It accelerates in a decreasing fashion over 5 time units. The acceleration, y double prime, from 0 to 5 is given by 4 minus t. And then has a constant deceleration from that point forward. Past time 5, y double prime is just the constant, negative 1. What we do is we begin by taking a Laplace transform of the left, just y double prime. This is pretty straightforward. We've done it many times by now. The Laplace transform of y double prime is s squared Laplace transform of y minus y prime of 0 minus s times y of 0. And using our initial conditions, this is just s squared times the Laplace transform of y minus 15. Now the forcing function on the right is first written like this, okay? f0 is the first piece, that's 4 minus t, and f1 is the second piece, which is minus 1. So what we do is we define our functions g. We start off by letting g0 just be equal to f0, that's 4 minus t. And then, according to the formula introduced earlier, g1 of t is f1 of t plus 5 minus f0 of t plus 5. The 5 coming from, that is the time at which the next function is introduced. f1 of t plus 5 is just minus 1, because that's what f1 is, it's constant. And f0 of t plus 5 is 4 minus the variable t plus 5. This simplifies down to just being t. So g1 of t minus 5 is f1 of t minus f0 of t, means the forcing function can now be written as g0 of t, the first bit, and then at time 5, add in the function g1 of t minus 5. The function we are adding in cancels out the f0 and introduces in the f1, where these plus 5s are exactly meant to counteract this one right there of a minus 5. So overall, we have g0 of t plus u of t minus 5, g1 of t minus 5. So since we've written the forcing function in this nice term, okay, where we have computed g0 of t is 4 minus t and g1 of t is t, by the second shifting theorem, now we can take a Laplace transform very directly. So first, the Laplace transform of g0, that's just the Laplace transform of 4 minus t, 4 over s minus 1 over s squared. And then what about the Laplace transform of u of t minus 5, g1 of t minus 5? By the second shifting theorem, it's just going to be e to the minus 5s times the Laplace transform of g unshifted. And the Laplace transform of t is just 1 over s squared. So the Laplace transform of our forcing function is seen to be 4 over s minus 1 over s squared plus e to the minus 5s times the quantity 1 over s squared. Observe that the forcing function is defined piecewise. Its Laplace transform is not. The Laplace transform of the forcing function is just this function right here. So now we combine that with the Laplace transform of the left that we took on a previous slide. And here we have it. This is the Laplace transform now of our differential equation. So here was the Laplace transform of our differential equation. And again, I just want to point out the beauty of the Laplace transform on the right-hand side being the forcing function was originally defined piecewise. However, the Laplace transform of the forcing function is not piecewise defined. It's just what's on the right. But now we can solve for L of y. The Laplace transform of y, once we divide out s squared to every term, is 15 over s squared plus 4 over s cubed minus 1 over s to the fourth plus e to the minus 5s times 1 over s to the fourth. Then we can just take an inverse Laplace transform of both sides. On the left, we get y. Inverse Laplace transform of 1 over s squared is just t. Inverse Laplace transform of 2 over s cubed is t squared. Inverse Laplace transform of 6 over s to the fourth is t cubed. And then here we're applying our shifting theorem again. We recognize this right here to be the Laplace transform of t cubed over 6. But it's being multiplied by this exponential, so when I take an inverse Laplace transform, we end up with this step function, u of t minus 5, and then instead of t cubed over 6, it's t minus 5 over 6. So here's the solution we have so far. What we can do, if we want to, is take this and present it in a standard piecewise way. So this solution, y, is 15t plus 2t squared minus t cubed over 6, and then at time 5, we introduce t minus 5 cubed over 6. So between 0 and 5, the step function is 0. We just get 15t plus 2t squared minus t cubed. Once the step function is introduced, however, we add in the term t minus 5 cubed over 6, which we expand like this. Simplifying down, the left bit plus this new expanded t minus 5 cubed over 6 means from t 0 to 5, we just have these three terms. But once we hit t being 5 and beyond, we have all of this combined with these, gives us negative 125 over 6 plus 55 over 2t minus 1/2 t squared. So if you don't want to write your solution in terms of step functions, you can convert it back into a piecewise defined function. Now here's the function, piecewise defined, that we managed to see was the solution to this initial value problem. What I want to point out is that on the first segment here, the second derivative of this is exactly 4 minus t. And the second derivative of this second piece is exactly minus 1. So this piecewise defined function from 0 to 5 has second derivative 4 minus t. From 5 and on has second derivative minus 1. Also, this first piece, if you plug in t equals 0, gives you y equals 0, matching the initial condition y of 0 equals 0. Also, the derivative of this, if you plug in 0, would give you 15, matching y prime of 0 is 15. Also, if you follow this function through time 5, you would end up with y of 5 is 625 over 6, and y prime of 5 is 45 over 2, which exactly matches this right here. This second piece also satisfies y of 5 is 625 over 6, and y prime of 5 is 45 over 2. This hints at a way to do these sorts of problems without bringing Laplace transforms in at all. What you would do is you would solve this initial value problem, y double prime equals 4 minus t, y of 0 equals 0, y prime of 0 equals 15, and you would get this solution right here. Then what you would do is you would follow this solution through time 5. You would then solve y double prime equals minus 1, which is solved with this function right here, as soon as you match the initial conditions, that at time 5, we want the value of the function to be 625 over 5, and at time 5, we want the derivative to be 45 halves. So it's possible to do these piecewise defined forcing functions without bringing Laplace transforms in at all, but every time you have a new piece, you essentially have a new initial value problem to do. So in this case, where there was really only two pieces, doing it piecewise or doing it with Laplace transforms is not a huge difference in terms of difficulty, but as soon as there's lots and lots of pieces going around, rather than solve 28 different initial value problems, we can just do one problem by introducing these step functions and using a Laplace transform. For a second example, let's do another initial value problem. Y double prime plus y prime minus 2y. Well, from 0 to 4, it's 4. From 4 to 8, it's 8 minus t. Beyond 8, it is 0. With initial conditions, y of 0 and y prime of 0 are both 0. Well, step 1, identify the specific forcing functions and times at which they occur. So the forcing functions are 4, 8 minus t, and 0, occurring at times 0, 4, and 8, respectively. So now we can define our functions gi, where g naught is f naught, and after that point, gi is given by fi of t plus ti plus fi minus 1 of t plus ti. So g1 of t is f1 of t plus t1 minus f naught of t plus t1. Now f1 was 8 minus t. So since t1 is 4, f1 of 8 minus t plus 4, then I subtract f naught of t plus t1, but f naught is just the constant 4, so t doesn't really matter. So overall, we get 8 minus t plus 4 minus 4, which actually reduces to a nice simple minus t. Then g2 is f2 of t plus t2 minus f1 of t plus t2. f2 is just 0. f1, as already discussed, is 8 minus t, but now we have t plus 8 here. So I have 0 minus 8 minus t plus 8. The 8's cancel, and this is just t. So now our forcing function can be written as u of t minus t naught g naught plus u of t minus t1 g1 plus u of t minus t2 g2. Now that we've written our forcing function in this nice convenient form, by the second shifting theorem, the Laplace transform can easily be taken, and we end up with e to the s t naught times the Laplace transform of g naught. E to the st1 times the Laplace transform of g1, e to the st2 times the Laplace transform of g2. We already found that g naught of t is 4, g1 of t is minus t, and g2 of t is just t. Therefore, the Laplace transforms respectively are 4 over s minus 1 over s squared and 1 over s squared. So here are the Laplace transforms we've computed so far. With t naught being 0, t1 being 4, and t2 being 8, the Laplace transform of the entire forcing function is now represented simply as 4 over s plus e to the 4s minus 1 over s squared plus e to the 8s times 1 over s squared. Now we're going to take the Laplace transform of the left. We end up with S squared times the Laplace transform of y minus y prime of 0 minus sy of 0 plus s times the Laplace transform of y minus y of 0 minus 2 times the Laplace transform of y. Now with our initial conditions that both y of 0 and y prime of 0 are 0, this simplifies rather nicely to just s squared L of y plus s L of y minus 2 L of y. We can go ahead and factor our Laplace transform out right now, and we have s squared plus s minus 2 times the Laplace transform of y. It's worth noting that when you're given the initial conditions y of 0 and y prime of 0 are both 0, then whenever you take the Laplace transform of any constant coefficient system like this, a y double prime plus by prime plus cy, you're just going to get as squared plus bs plus c times the Laplace transform of y. It's a handy thing to remember. Provided, of course, those constants are the coefficients. If your coefficients on y prime, y double prime, and y aren't constant, then things can get a little tricky, but when you have constant coefficients, this is all there is to it, provided the initial conditions were that y of 0 is 0 and y prime of 0 is 0. Okay, so we've taken a Laplace transform of both sides, so we can set those equal to each other. On the left, we had s squared plus s minus 2 times the Laplace transform of y, and on the right, 4 over s plus e to the 4s times minus 1 over s squared plus e to the 8s times 1 over s squared. Now we're going to divide both sides by s squared plus s minus 2. We're going to end up with three different terms, 4 over s divided by this, e to the 4s with a minus 1 over s squared divided by that, and e to the 8s with 1 over s squared divided by the same thing. Each of those three terms we're going to do partial fraction decomposition of. Thankfully, these two are essentially the same thing, it's just up to a minus sign. So, for the first term, 4 over s, when you divide by s plus 2, s minus 1, the partial fraction decomposition gives these terms. For e to the 4s times minus 1 over s squared, once you divide by s squared plus s minus 2 and perform partial fraction decomposition, here's what you'll end up with. And the third term is essentially the same, just with a minus sign. Okay, here I had a minus, here we have a plus, so if here we had a plus, here we're going to get a minus. So there is all the partial fraction decomposition. So we're staring at this ugly mess. The Laplace transform of y is all of these terms put together. But with some perseverance and a table of Laplace transforms and the second shifting theorem, we can work through term by term. So we're going to take an inverse Laplace transform of both sides. On the left, we just get y. Inverse Laplace transform of minus 2 over s is just minus 2. Inverse Laplace transform of 1 over s plus 2 is e to the minus 2t, and we've got that factor of 2/3. Inverse Laplace transform of 1 over s minus 1 is e to the t with that factor of 4/3. Now let's move on to these terms here, where I have this exponential term times some otherwise familiar looking bits. So this 1/2 stays there. The inverse Laplace transform of 1 over s squared would typically be t. But since it's being multiplied by this exponential, I get a step function and a t minus 4. Similarly, the inverse Laplace transform of 1 over s would typically just be the constant 1. So I get the 1/4, but because it's being multiplied by this exponential, we end up with a step function, a 1/4, and the constant 1 evaluated at t minus 4 doesn't really matter there. Here, 1/12, 1 over s plus 2. Inverse Laplace transform of 1 over s plus 2 would typically be e to the minus 2t. But because it's being multiplied by this exponential here, I end up with a shift function, and instead of getting e to the minus 2t, it's e to the minus 2 t minus 4. Finally, this 1/3 hangs out, and instead of the inverse Laplace transform just being e to the t, it's going to be e to the t minus 4, again, times this step function, which has been factored out of everything. Similarly, the last terms look very, very similar. They are all the same fractions because the partial fraction decomposition was the same. However, they're being shifted by 8, so all of these shifts are by 8 instead of 4. So our solution has been found to be the sum of all of these various terms. We're not going to attempt to write this as a piecewise defined function. It's not incredibly onerous to do so, it's just really not required. So here is our solution, and we're not going to bother trying to write it as a piecewise function. And a third example, solve the initial value problem. Y double prime plus y is the absolute value of the sine of t, where y of 0 is 0 and y prime of 0 is 0. Now we've already remarked that with initial conditions y of 0 and y prime of 0 both being 0, the Laplace transform of the left is just going to result in 1 plus s squared times the Laplace transform of y. That's straightforward. The interesting part of the problem is definitely that forcing function, the absolute value of sine. Now the forcing function is periodic, but not with period 2 pi, with period pi. Because we have an absolute value of sine, it's just a bunch of little hills over and over again, repeating with period pi. Okay, because the sine of t plus pi is typically minus the sine of t. Since we're an absolute value, that minus sign doesn't matter. So we have a periodic function with period pi. So since we have a periodic forcing function, we're going to use that entry in our table of Laplace transforms. The Laplace transform of this periodic function will be the integral of e to the minus st absolute value sine over one full period, 0 to pi, over 1 minus e to the negative s times the period, which is pi. So all we have to do is evaluate that integral in the numerator. Now from 0 to pi, the sine function is positive, so the absolute value is redundant. Referring to a table of integrals tells me that the integral from 0 to pi of e to the minus st sine of t dt is negative e to the minus st s sine t plus cos t over s squared plus 1, evaluated at pi and 0. Now, thankfully, both pi and 0 result in these sine terms being 0, so that can safely be ignored. What you end up with your cosine terms, which are negative 1 and 1 respectively, this all simplifies down to just being e to the minus pi s plus 1 over s squared plus 1. So overall, setting the left equal to the right, now that we've taken the Laplace transform of the absolute value of sine y, we have this. 1 plus s squared times the Laplace transform of y is what we just computed. Dividing s squared plus 1 over to the other side, we have the Laplace transform of y is e to the minus pi s plus 1 over s squared plus 1 all squared. From a table of Laplace transforms, we see that the Laplace transform of sine t minus t cos t is 2 over s squared plus 1 squared. This is an entry that has s squared plus 1 squared down in the denominator. So overall, we're going to represent this as, first, we have an e to the minus pi s times constant over this denominator. That's a shifted form. Step function at pi, sine of t minus pi cos of t minus pi. So all of this simply comes from e to the minus pi s times 1 over s squared plus 1 squared. And of course, this factor of 1/2 is necessary to cancel out the 2 that would have appeared here. Then I have a 1 over s squared plus 1 squared, from which I get the sine t minus t cos t. So I have to split this up into two terms, an exponential over this denominator and a constant over this denominator. The exponential over something that I know how to deal with gives me this step function shift from the second shifting theorem, and the 1 over s squared plus 1 simply gives me this sine t minus t cos t. And there's our solution y. And again, we're not going to represent this as a piecewise defined function. It's perfectly happy to live its life in this step function representation. So altogether, earlier, we worked through how to take the Laplace transform of step functions. We used that to figure out how to take Laplace transforms of piecewise continuous functions. And now we've seen how to take that knowledge to solve linear differential equations with piecewise continuous forcing functions. The main tool was the second shifting theorem, where the Laplace transform of a step function times another function, both shifted by the same amount, is equal to an exponential times the Laplace transform of the unshifted function g. Now, in all of the examples we've done, the differential equation only had constant coefficients. This is because at this point, all we know how to take Laplace transforms of are y prime or y double prime, and using linearity, constants can factor out. If we had something like t times y prime, it would get a bit more complicated, but more on that later.